Okay, so I'll hit that record. So colleagues, very warm welcome to today's ZAG seminar. So my name is Jared Ongaro. I'm from Nairobi, Kenya. I work at the University of Nairobi, and I'm delighted to be the host for today's seminar. So our speaker today is Eiji Inoue, a special postdoctoral research member in mathematics at Lincoln Interdisciplinary Theoretical and Mathematical Science Program, and is going to talk about Bellman entropy and optimal degeneration. So Eiji, the floor is yours. Thank you very much.
Okay, thank you for introduction, and I'd like to thank the organizers for giving me a chance to talk at this seminar. Okay, today I'd like to talk about mu-csck metric and mu-stability, which I introduced to understand csck metrics and Kahler-Ricci solitons in a unified way. And I especially focus on non-Archimedean mu entropy, which is related to mu-stability and H entropy for Fano manifolds. And it is the story is deeply related to Perelman's entropy. So I'd like to explain its relation with Perelman's entropy in the final section. Okay. Okay, I firstly explain about model story of this talk, which is on optimal degeneration along Kahler-Ricci flow. I believe this helps you to understand the motivation for mu entropy of today's topic. Okay, let's begin with chance one's result on the Gromov-Hausdorff limit along of Fano manifolds along Kahler-Ricci flow. Let X be a Fano manifold and omega be a Kahler metric on X. Then chance one proved there exists consider the Kahler-Ricci flow, normalized Kahler-Ricci flow starting from this initial omega. Then they proved there exists a Gromov-Hausdorff limit along Kahler-Ricci flow, and it is a Fano variety endowed with a Kahler-Ricci soliton, which is a Kahler metric satisfying this equation for some holomorphic vector field. And I note this equation is a generalization of Kahler-Einstein equation, as if you substitute C0, then this equation is nothing but the Kahler-Einstein equation. And I also want to note that the pair of omega hat and Xi satisfying this equation is unique modulo the automorphism group of X hat. Okay, and they also proved, they also constructed algebraic objects, two algebraic objects. The one object is the filtration on the anticanonical ring of X. For filtration, we can associate graded algebra, and we can consider its project. And they also proved that this X bar is this graded algebra is finitely generated, and X bar is its project. X bar is a modified k-semi-stable Fano variety. Here, modified k-semi-stability is related to the existence of Kahler-Ricci soliton as k-stability. Usual k-stability is related to the existence of Kahler-Einstein metric. And the second object is the degeneration of X bar to the Gromov-Hausdorff limit X hat, which is an R equivariant. So filtration generates R action on the central fiber, and we can construct an R equivariant special degeneration of X bar, whose central fiber is the X hat and the Gromov-Hausdorff limit. And the allocation extends to x hat, and the corresponding allocation is nothing but the one parameter subgroup generated by disk C. Okay, this is what chancellor 1 constructed. And so it relates, so these two-step degenerations relates x with x, the Gromov-Haus limit x hat by two-step degenerations in an algebraic way. So we want to characterize this filtration and this degeneration in a purely algebraic words, purely algebrogeometric words. And the second degeneration is one can believe the second degeneration is can be treated in a framework of modification. Maybe can you hear now?
We lost you, I think, for some couple of like a minute. Yeah.
Okay, now but slide is not shared. Okay. Can you see the slide?
They're coming. Yeah, sure.
Okay. Sorry.
Oh,
And they introduced a H invariant of filtration, which today I call H entropy of filtration, which it is defined by this equation. Here, DHF denotes the Duesmat-Heckman measure associated to the filtration, and AX denotes the log discrepancy of valuation, and phi F denotes the potential of the non-Archimedean PSH metric associated to the filtration, but it can be also characterized by this equation. Okay, we take infimum of the among all the quasi-monomial valuations, and then the invariant is defined by this equation. Okay, their claim is that chancellor 1's degeneration, chancellor 1's filtration maximizes this H entropy, and they also prove this equality for the supremum of the H entropy equals to the infimum of some Archimedean functional. Okay, and Hanley proved that the maximizer exists. Maximizer is unique if it exists. Actually, they also proved the existence. The maximizers are unique, and so that the X bar, so that the filtration is uniquely characterized as a maximizer of this H entropy. Chancellor 1's degeneration can be characterized as the maximizer of H entropy. And so that X bar omega is independent of the initial metric of the Kahler-Ricci flow. So we can attach, so in other words, we can attach for each Fano manifold, we can attach modified pk-semistable.
Excuse me.
Yes. Hi.
Can I see the previous page?
Previous page.
Yeah.
Is it okay? Can I go back?
Did you cover this one or not? You covered, right? I see. Oh, okay, thank you.
Okay, thank you. And so we can characterize the central fiber of the degeneration filtration. The central fiber of the filtration is uniquely characterized by this H entropy. And recently, Bloom issued one proved that even when X is singular, there exists so the groove is this associated graded algebra, and this is finite. They proved this is finitely generated even when X is singular, and the associated scheme is actually modified k-semi-stable form variety.
Excuse me.
Hi.
What is AX omega? Second line.
AX of omega.
W. Second line. Yeah.
This AX is the log discrepancy of W. W is a valuation.
So did you define that one or not? Where did you define AXW?
I didn't define the AXW, but
define,
it's the usual notation on log discrepancy for algebraic geometries. I guess.
Okay.
So it is called log discrepancy. So you can find the definition in some reference, I guess.
Okay, thank you.
Okay, so we are motivated to study H entropy from these studies. Okay, today I want to talk about another entropy, which I call mu entropy. It is related to H entropy, but it is defined for general polarized manifold beyond finite manifold. Okay, let me give a brief explanation on mu-c-ck metric and mu-k-stability. Okay, recall that c-ck metric is a natural generalization of Kahler-Einstein metric to general polarized manifold. So the question is, what is natural generalization of Kahler-Ricci soliton to general polarized manifold? So in view, there are two nice aspects on Kahler-Ricci soliton. The first one is k-stability, and the second interesting aspect is optimal degeneration, as we saw in the previous slide. And these notions are based on these differential geometric background. So if you want to consider k-stability, we want moment map picture on Kahler-Ricci soliton, and if you want to consider optimal degeneration, we want to volume minimization on Kahler-Ricci soliton, which I didn't explain still, but okay, I will explain in the next slide. And this leads to the notion of mu-c-ck metric. Mu-c-ck metric possesses these two pictures. Okay, here's the definition of mu-c-ck metric. Kähler metric omega on a Kähler manifold is compact Kähler manifold is called a mu-c-ck metric. Mu lambda c-ck metric, where lambda is a real number and c is a holomorphic vector field, and mu c is the Hamiltonian potential associated to the imaginary part of disk C. Okay, then we consider this curvature, scalar curvature, and the Laplacian, half of the Laplacian of the Hamiltonian potential, and complex gradient, the square norm of the complex gradient. And we call Kähler metric omega is mu lambda c-ck metric if there exists lambda and c satisfying this equation. And this notion generalize Kähler-Ricci soliton. Actually, in this Kähler class, the Kähler-Ricci soliton is equivalent to a specific choice of mu lambda, a specific choice of lambda. Kähler-Ricci soliton is equivalent to mu-c-ck metrics for some specific choice of lambda. Here is lambda. And so it's a generalization of Kähler-Ricci soliton. And if you take C to be 0, then This scalar curvature is nothing but the usual scalar curvature. So this generalizes, this notion also generalizes CSCK metric. And we can show it's not trivial, but surprisingly, we can connect extremal metric and mu CSCK metric in some way by considering the limit of lambda going to minus infinity. And then we can show if there exists an extremal metric in the Kahler class you consider, then you get mu lambda CSCK metric for sufficiently small lambda and for some vector field C for each lambda. In the same way.
Could I ask, so what is mu-Xi? So Xi is a holomorphic vector field, and
yes, mu-Xi is the Hamiltonian potential of the imaginary part of Xi.
Okay, yeah, thanks.
Okay. And okay, so if you have an extremal metric, there also exists a mu lambda CSK metric for sufficiently small lambda. And there is a moment bound picture for mu CSK metric. We consider a symplectic manifold with a torus Hamiltonian torus function and take a vector from the Lie algebra of T and the real number R. Then consider the symplectic manifold, infinite dimensional symplectic manifold, which consists of T invariant almost complex structures. There is a symplectic structure modified by Xi, which uses the measure exponential, this measure, which uses this measure in the definition. And we have a Hamiltonian torus, we have an action by T equivariant, the group of T equivariant Hamiltonian diffeomorphism group. Okay, then the mu scalar curvature gives a moment map for this action. So this moment map picture characterizes mu CSCK, the notion of mu CSCK metric modular constant. And from this picture, we are naturally motivated to introduce mu Futaki invariant, mu lambda Xi Futaki invariant by this definition. It is defined for a vector field. But we can generalize it to the test configuration, invariant for test configuration, using an equivariant intersection formula on this mu Futaki invariant. Okay, today I don't explain much about mu-k stability, but there is a natural step to introduce the notion of mu-k stability. And mu-k stability includes the notion of modified k stability for Kahler-Ricci soliton, and we can show if if polarized manifold admits a mu CSCK metric, then it is mu-k semistable. And Apostol, Schubert, Lodi also proved that it is mu-k polystable with respect to smooth configurations. Okay. Here's another aspect of mu CSCK metric, volume minimization. This proposition generalizes Tianju's volume minimization argument for Kahler-Ricci soliton. If we have a Hamiltonian action by a compact group on the Kahler manifold, we can consider, we can construct a functional on the Lie algebra of this Lie group, which satisfies the following properties. Its derivative at Xi. If you take Xi, we can consider its derivative, then it defines the functional, defines a element in the dual of K, and then the statement is it is Futaki invariant at Xi. And it is proper and bounded, the functional is proper and bounded from above. So it admits, so it always admits maximizer. And so it follows that there always exists a vector field with vanishing Futaki invariant. And and we can see the uniqueness for sufficiently small lambda on each x, but it turns out the vector field satisfying this this condition is not necessarily unique for large lambda, even on the simplest variety CP1. Even on the simplest variety CP1, if we take greater lambda, then we find non-trivial C with vanishing Futaki invariant. Okay, this is what I call phase transition. Today I don't talk much about this, but what you should be in mind is the existence of vanishing Futaki invariant. Okay, I'd like to talk about non-Archimedean mu entropy and its relation with stability. Non-Archimedean mu entropy is a generalization of this functional to general test configurations, and it's related to H entropy. Okay, here is a definition of characteristic mu entropy. We consider the equivalent. This is equivalent index, which is also defined by this measure. And we have an expansion of equivalent index thanks to the equivariant Riemann-Roch theorem, and we can expand it like this. The first term is the integration of exponential with respect to the reduced Heckman measure. And the second term is some intersection with respect to so-called homology canonical class. Homology, it's derived from homology third class, and it's equivalent homology third class. Okay, the definition of characteristic mu entropy is you use the coefficient of this expansion. We use the first term and the second term in the definition of mu-check. Here XL is a test configuration and tau is a non-negative real number. Here is the definition, and we also define sigma check by this integration with respect to this Heckman measure. And we can also compute this mu check by equivariant intersection with respect to the equivariant canonical relative canonical divisor over on the compactification of a test configuration. We can also compute in this way, but okay, here's the definition uses just uses a coefficient. And we put mu check lambda to be we define mu check lambda by this equation, mu check plus lambda sigma check. Okay, this is the characteristic mu entropy. And there is a variant, which I call non-Archimedean mu entropy, which uses the log equivalent canonical divisor instead of the usual canonical divisor. This invariant fits into the formulation of non-Archimedean pluripotential theory rather than this invariant, as non-Archimedean Markovitch invariant fits into the non-Archimedean pluripotential theoretic framework rather than Donaldson-Futaki invariant. And we define the mu entropy for lambda to be the mu check NA plus lambda sigma check previous sigma check. And it satisfies this equality. So this is nice property for mu check NA for any lambda. Sorry, we have this equality for any lambda, and this is nice in view of in order to fit our framework to non-Archimedean pluripotential framework. Okay, so since this invariant will fit into non-Archimedean pluripotential framework, we call it non-Archimedean mu entropy. And we can compute non-Archimedean mu entropy for toric test conflation by simple integration. If you have a toric variety, consider its moment polytope and consider toric test conflation associated to some piecewise linear convex function. Then the mu entropy, non-Archimedean mu entropy of test conflation can be computed by this integration. Okay, so you can, if you have an explicit example of toric test conflation, you can compute the non-Archimedean mu entropy. Okay. Now we'd like to consider the differential of the mu entropy, characteristic mu entropy. We want to prove that the differential of mu entropy is the mu Futaki invariant of test conflation as a generalization of this result. So since non-Archimedean mu entropy generalizes functional, we want some generalization of this result, and we have such result. And we want to, in order to state the claim, we introduce the notion of perturbation of test configurations. It is which I call polyhedral configuration. Okay, consider strictly convex full-dimensional cube polyhedral cone in a finite dimensional space, and consider the associated affine toric variety B sigma. This condition implies that there exists a unique fixed point in B sigma, which we call the origin, or we call the fiber over the point as the central fiber. Okay, polyhedral configuration is a triple of T equivalent projective flat family X over some B sigma, and relatively a T equivalent relatively amplitude bundle L on X, and a vector in the cone, and a triple of these information. And we know polyhedral configuration defines a finitely generated filtration by this equation. And for finitely generated filtration, we can define the mu character, characteristic mu entropy similarly as the characteristic mu entropy for test configurations. So we just use such expansion. And then the typical example. Okay, so test configuration is an example of polyhedral configuration. Of course, it is associated to n. We take n to be z, and sigma to be the half line, and then B sigma is the affine plane, affine C, and the definition is nothing but the test configuration. And this information is the information on the non-negative real number, which we used here. We used in the we use here. So test configuration defines a polyhedral configuration, and we can also construct a polyhedral configuration in these ways. If you have a torus action on a polarized manifold, then take a vector C in the Lie algebra of T and a cone containing disk C. And you consider the product endowed with the diagonal action. then this provides polyhedral conflation. Okay, this is an example of polyhedral conflation. It represents the this vector. Okay, it represents the action of this vector. Okay, and another example is if you have a t-equivariant test conflation, we can consider the product of B sigma times the test conflation, and we can endow T times C star action on this product by, as for T, it acts diagonally, and as for C star, it only acts on X, and it acts trivially on B sigma. And it provides polyhedral configuration for sigma times the half line. Okay, and we denote the associated, okay, we consider the vector C plus tau eta for non-negative tau, which is a vector in sigma times 0 infinity. And we denote the associated filtration as fc plus tau xl. And we can easily show that the differential of mu entropy with respect to this curve is nothing but the mu Futaki invariant at C to the direction of XL. Okay, so we can understand this as a derivative. Okay, and the consequence of this proposition is if the characteristic mu entropy is maximized some vector among all filtrations, then among all polyhedral configurations, then the polarized manifold must be mu-k semistable, because if it is maximized at C, then this mu entropy, the differential must be non-positive. So this minus Futaki must be non-positive, and it implies the Futaki invariant is non-negative. Okay, so this is the definition of mu-k semistability. Futaki invariant is non-negative. Okay, and actually the characteristic mu entropy is actually maximized by some vector field if you have a mu CCK metric for some negative non-positive lambda. Okay, this is non-trivial results, but we will explain in the last section. Okay, and we can extend the results to this situation. If you have a polyhedral configuration maximizing the mu entropy, then the central fiber of this polyhedral configuration must be mu-k semistable. Yeah, the proof is similar to this. We compute the differential. We can easily show this, relatively easily to show this, and then the question is, if we can show the existence and uniqueness of maximizers of mu lambda, then we can associate for any polarized manifold, we can associate some mu-k semistable polarized variety. Okay, so this is a question, and and okay, skip this remark, and here's my proposal for existence. Consider some completion of the space of filtrations and extend the non-Archimedean mu entropy to the completion as an upper semi-continuous function. Then you show the compactness of maximizing sequences of mu entropy. It will imply the existence of maximizer thanks to this upper semi-continuity. And then it shows the existence of some objects in the completion. So it may be not finitely generated filtrations, but my proposal is then prove the regularity of the maximizer. So it must be finitely generated filtrations, but we firstly show the existence in the completed space and then show the regularity. So this is similar to the approach by Minchen-Xia in the context of extremal metric. He shows the existence of optimal destabilizer of optimal destabilizer of Donaldson-Futaki invariant. He shows the existence in the space of E2, usually denoted as E2, which I will explain. Okay, here's my this is my current situation of this proposal. Okay, I proved there is a complete metric space denoted as eXp as a subspace of E1, which was constructed by Buxton Johnson as a completion of the space of test completions with respect to L1 null. And we consider all each null using exponential weights. And we can construct complete metric space as a subspace of this. This space is the space of non-Archimedean PSH metrics as illustrated in this graph. And there exists a complete metric space, and we can extend the non-Archimedean mu entropy to this complete metric space. Okay, which extends the mu non-Archimedean mu entropy for test conflations. So this is the current situation. Okay, and we can, okay, now I explain the relation with H entropy. We can also extend the H entropy as a functional on eXp. And we have inequality. We always have inequality. And as for optimal, as for the maximizer of H, we have the equality. Okay, this is current situation of my study on mu entropy. Okay, now I'd like to explain. Okay, so is there any question so far? Now I want to talk about differential geometric topic. So this is the end of algebra geometric topic. Is there any question?
Sorry, say again what eXp means. What does exp mean?
Exp so E1 denotes the completion with respect to L1 norm, and EXp denotes the completion with respect to all each norm associated to exponential weight.
I see. Okay, thanks.
So we use all each analysis. Thank you. Okay, so let's go further. Okay, I'd like to explain a relation with Perelman's entropy of our mu entropy. Okay, here's definition of Perelman's entropy. Slightly different from the original definition, but it is essentially equal to the Perelman's entropy modulo sign and constants. Okay, we consider, we take a Kahler metric and a smooth function. And for such a pair, we define functional for pairs of metric and functions. Perelman originally considered such a functional for general Riemannian metric, but restricting to Kahler metric is a key point of this story. And then we can regard, since the tangent bundle of the space of Kahler metric can be decomposed as, can be written as the product we can regard this functional as a functional on the tangent bundle of the space of Kahler matrix. And this is a nice viewpoint for W functional in our study. Okay, this is the definition of Perelman's entropy. Okay, originally Perelman's entropy was introduced in the study of Ricci flow and to study the non-collapsing behavior. Okay, but today we do not think about non-collapsing results. It's almost closed in our framework. Our story is almost closed in our framework. Okay, the first statement is the critical point of the W functional is precisely mu c-ck metric. Okay, the critical point. So we have a pair of Kahler metric and a functional smooth function, and we can consider the gradient of smooth functional. If this pair is a critical point of the functional, then we can show this vector field is holomorphic, and the Kahler metric is a mu lambda c-ck metric with respect to this vector field. And this is the first result, and on the relation of Perelman's entropy and mu c-ck metric, and consider the mu entropy. Originally, Perelman's mu entropy is infimum of W functional as the sign is reversed from our convention. Okay, but in our convention, we consider the supremum of W functional among all F. Okay, then if you consider such a functional, then it is not obvious if this functional is a smooth functional on the space of Kahler matrix, but we can show when lambda is not greater than 0, this is smooth function. This is actually a smooth functional. And we can consider a variation of this functional, then we can see the critical points of this functional is precisely mu c-ck metric. And this functional is analogous to, so this functional is analogous to Clave functional for extremal metric and H entropy for Kahler-Ricci solitons. In our context of mu c-ck metric. Okay, and the relation of mu entropy and H entropy is analogous to the relation of Mabuchi and Ding functional. On a Fano manifold, we always have this inequality, and the relation of mu and H is analogous to Mabuchi and Ding. Actually, we can see the derivative. Sorry, actually, we can see the derivative of W functional at f equals 0. It provides Mabuchi functional, and there is a similar functional for H defined on tangent bundle. And if you consider its derivative at f equals 0, then it gives the Ding functional. So it is actually closely related to this functional. Okay, and here's the relation with non-Archimedean mu entropy of our Archimedean mu entropy. There is an inequality for XL running all test calculations, and omega runs all Kahler metrics. Okay, this inequality is analogous to the equality on H functional, and I actually believe the equality holds, but so far I obtained the inequality result. So this is analogous to the inequality, Donaldson's inequality on Kahler functional. Okay, Now I'd like to sketch the proof of this result. We consider the doubly functional along geodesic rays associated to test conflations. This is the position of geodesic ray, and this is the velocity of the geodesic ray. So this is defined on tangent bundle, so it is natural to consider such variables. Okay, the first result is for any C11 regular geodesic, double functional is monotonically decreasing. To show this, we consider the action functional of W and show the convexity of this functional using a equivariant tensor calculus and Baumann-Bergson's subharmonicity argument on Bergman kernel. Okay, you're using based on Bergman kernel. Okay. So the proof is closely related to the convexity of merge functional. The difference is actually the tensor calculus on equivariant differential forms. Okay, and the next to show is the slope, the limit of double functional, which is the slope of this action functional, is equal to the mu entropy of test conflation. This can be shown for for some class of test conflations. We only consider smooth test conflations, and then we have regularity of geodesic ray across the central fiber, thanks to true to such point code. And then we can apply equivalent Stokes theorem using C11 regularity to show this equality. And we can compute this by equivalent intersection. So it can be computed by equivalent differential forms. Then we can relate this to this double functional. And from these two results, we know that by the definition of mu entropy, it is a superimable double functional with respect to this, where this runs all functional. We get this inequality at t equals 0. And since this is monotonically decreasing, we have this inequality for all t, and we can consider the limit of this entropy, this double functional. Then it converges to mu entropy, thanks to the second claim. Okay, this proves that for any Kahler metric on the test conflation, we have this inequality, which proves this theorem. Okay, and as a corollary, we obtain this result for non-positive lambda. All the critical points of the mu functional are global minimizers. And it is actually precisely mu CSK metric. And if there is a mu CSK metric for non-positive lambda, then we actually have equality of these two invariants. Because we have this equality for mu CSK metric. And it proves since this is greater than this infimum, not smaller than this infimum, and this is not greater than this. So this proves the reverse inequality of when there exists a mu CSK metric. Okay, this is a relation of double functional with mu entropy, non-Archimedean mu entropy. So this equality and this slope formula is explains a deep relation with non-Archimedean mu entropy. Okay. Okay, let us consider other frameworks. The first one is H entropy, and we can understand that these in a unified framework, not unified, in a similar way. We can understand H entropy and color functional in a similar way as we did for W functional. If you have a H functional, then introduce a functional on tangent bundle, where H is a rich potential and F is a arbitrary smooth function. And then we can show by Legendre duality, we can show the supreme of L is nothing but H. And we can also show the limits of this functional. The functional on the tangent bundle is gives non-Archimedean H entropy. So and we can also show that this is monotonically decreasing, similarly as the functional, which is based on the convexity of Ding functional, because this part is related to Ding functional. And we can also show the Donaldson's inequality for Calabi functional in a similar way. If you consider Calabi functional, we introduce functional on the tangent bundle defined in this way. And then we have the supreme of W extremo is nothing but the Calabi functional. And we can also compute the limit of the W functional, Wx, and then it gives some invariant of test conflation. And we can see if the Donaldson-Futaki invariant of XL is non-positive, then we can see the maximum of this invariance taken over all non-negative tau is the Donaldson-Futaki, the Donaldson-Futaki invariant divided by L2 norm. Okay, so this is a way to understand the inequality on H entropy and mu entropy and Calabi functional in a unified way. Okay, this is the end of my talk. Thank you for listening.
Okay, thank you very much. I think we can all thank our speaker for the wonderful talk. There are two ways we can do it. We can either mute and do it in the natural way, or we can use the reactions on Zoom. Yeah. So thank you very much, Eiji. So I think we have time for questions, and if you have a question, there are two options again. You can either put it on the chat, or you can actually speak on it. So welcome for the questions.
So this question on maximizers of the non-Archimedean mu entropy, can you say anything about the toric case of that problem?
No existence results so far, even in explicit example, unfortunately. Actually, mu entropy is not so easy to compute because it is concerned with exponential of convex functional. This integration is not so easy to compute, I guess. So I have no idea in explicit examples so far.
And if you did have a maximizer in the toric case, would you get some kind of, like I'm thinking of Saikei's paper where if you have an optimal degeneration, then it splits the polytope up into relatively k semi-stable polytopes. Would you get some kind of other decomposition of your toric variety into semi-stable pieces or something? Or
so semi-stable piece. My current result is if the mu entropy is maximized by some polyhedral conflation, the central fiber is mu k semi-stable. This is this is what I know so far. And I don't know any explicit example of maximizing configuration, actually, unfortunately.
Thanks.
Thank you.
Yes, Maria, please go ahead. Mario, sorry. Mario, please go ahead.
Yeah. Hi, I have a question. So
Yeah.
in the definition of this quantity mu, after when you introduce the functional, you define mu as a supremum, right? Over functions which integrate to one. Is that correct?
Sorry, sorry.
When you define in the differential geometric part, when you define your mu as a supremum, yeah,
Yeah,
using
yes.
this.
So
Yeah,
if you find, so your question is if you find a differential geometric part of mu,
I'm curious because in the work of Perelman, you use the infimum over the functions with mean value 1 to define a quantity which is increasing along Ricci flow. So I wonder if there is any conceptual difference from the fact that here you're taking the supremum instead of an infimum. I wonder if there is something.
This is the sign is reversed from Perelman's definition.
Oh, okay, it's just that. Okay, I see. So it's really the same. It's really the same quantity.
Yeah. So really same Perelman's mu.
Okay, thanks. Sorry.
Thank you very much.
Thank you. Do we have more questions, please?
I had another question about the moment map picture and the geodesic. So in the moment map, you end up using a different volume form, I guess, on the space of Kahler metrics. So why doesn't that lead to a different notion of geodesic? Or are the geodesics you get the same as the usual geodesics in the space of Kahler metrics?
GeoGZ. Well, what is GeoGZ?
The geodesics. Like this in the usual case, the solutions to the homogeneous Monge-Ampere equation, like the geodesic. Geodesic, maybe.
I don't know the notion, unfortunately, I guess. So, what was your question? What was your question? Once again, please.
So at some point in your talk, you were differentiating these functionals along certain paths in the space of Kahler metrics. And I guess these were geodesics, the paths that you were associating to a test configuration.
So, are you talking about a moment picture?
Well, I was just wondering about, so if you go to the differential geometry, just keep going and I'll tell you when to stop. Further on into the bit where you had the W functional and relating that to algebrogeometric numbers. Yeah, never mind. It's not so it's not important.
Okay, so sorry for that. Please ask me again later by mail or something.
Can I ask one simple question about your talk? So in the last part, you mentioned that you just show that the inequality between superior of non-Archimedean mu hat. Yeah, these guys. And so you do not show that the equality itself.
So not for all x, but in some special case we have equality. If you have a mu-Siseki metric, then we have equality. But I believe equality always hold. Independent of the existence of mu CSQ metric. But so far, we only know this case.
So that you can still expect that your equality will hold.
Yes, I believe. And it's a conjecture.
But for example, Hisamoto or Donaldson already show that equality case. So that
not for mu entropy, but he proved the equality for Mabus solution, functional associated to Mabus solution. So and in the proof, he uses the inverse Monge-Ampere flow, I guess. And we need some notional flow related to the functional. And in the case of Calabi functional, we can use Calabi flow. And in the case of Mabus solution, we can use in the inverse Monge-Ampere flow. And in the case of H entropy, we can use Kahler-Ricci flow to show the equality. But I don't yet consider the notion flow notion associated to mu functional. I guess there is a flow equation, so-called mu flow, but I've not yet considered about it.
So that Hisamoto's argument here technically uses inverse Monge-Ampere for
yes
to show that this equality. But in your case, there are some technical issues for applying.
Yes, so for instance, we may be able to consider the gradient of this functional, and we should show the existence of the flow in the global time. And but this functional is not explicitly written because the definition is supremum mode of the functional. So it seems to me the flow is not so easy to treat. But I believe there is a notion of flow associated to mu, and equality must hold, I believe.
I see. Yeah, thanks.
Thank you very much.
Okay, I believe we don't have another question. So let's thank our speaker again. Thank you very much. And we do this again on Thursday on seminar on e-csck connection for bundles. So hope to see you at the same time. Thank you very much.
Thank you very much.
Thank you very much.